Hello everyone, my name is Pratyush and today we will be solving question 2 of the 2026 AB Physics C Electricity and Magnetism FRQs. So let's get right into it. So question 2 asks us, thin non-conducting rods S and T are held fixed in the XY plane as shown in figure 1. Rod S is oriented along the x-axis in the region minus 3L less than or equal to x less than or equal to minus L. Rod T is oriented along the y-axis in the region L less than or equal to y less than or equal to 3L. Each rod has uniform positive linear charge density, positive lambda. Point P is located at minus 2L, 2L. Okay, so complete the following tasks in figure 2. Draw an arrow starting on the dot that indicates the direction of the net electric field at point P due to rods S and T. Draw an arrow starting on the dot that indicates the direction of the net electric field at the origin O due to rods S and T. And draw an arrow starting on the dot that indicates the direction of the net acceleration of a small negatively charged sphere, not shown immediately after the sphere is released from origin O. Okay, so let's take a look. So first it wants us to draw the net electric field at point P due to rods S and T. So because it has positive linear charge density, it's given, so we know that both of these rods are positively charged. So that means the electric field lines will be pointing away from these rods because that's the convention for positively charged for positively charged uh, uh objects and particles, things like that. So from rod T, so let's kind of draw the grid here for point P. So to understand the net electric field, we need to understand the components of the electric field supplied by each rod. So from rod T, the electric field at point P will be directly to the left because point P is directly to the left of rod T, and because we can assume the electric field is almost uniform because it's a rod and it's pointing away from the rod because it's positively charged, the electric field is going to be directly to the left. And I'm just going to draw the components here just for reference, but our actual answer should only be the net electric field. So then now let's understand the component of the electric field provided by rod S. So rod S is directly below point P, and similar to rod T, we can assume it's a almost uniform electric field at point P, and because it's also positively charged, it'll be pointing straight up the electric field from rod S. So it'll be pointing straight up. So we can see that these are the two components of the electric field. So because these are two components of the electric field, the net electric field will be pointing at an almost 45-degree angle up and to the left at point P. Okay? So now it's asking draw an arrow starting on the dot that indicates the direction of the net electric field at the origin O due to rods S and T. Okay, so this is a very similar process. So at origin O, we have to identify and understand the components of the electric field provided by each rod. So by rod T, the component of the electric field is going to be pointing straight down, and by rod S, the component of the electric field at the origin is going to be pointing straight to the right. So we're going to get a net electric field pointing diagonally down and to the right at the origin. So now it's asking us for the net acceleration of a small negatively charged sphere immediately after the sphere is released from rest at the origin O. Okay, so it's important to understand the net charge of the sphere, which is negative. And because the net charges of the rods are positive and opposites attract, the sphere will move towards the rods rather than away. So that's important to understand first. But now we should understand the net direction of the acceleration. So the net direction of the acceleration is going to be in the direction of the force, the direction of the net force. And so we need to understand the components of the force that each rod applies on the sphere. So the sphere is at rest at the origin, and at the origin, because the sphere is negatively charged, rod S applies a component directly to the left, a force component directly to the left of the sphere, and rod T provides a component directly up to the sphere. So we want to be drawing the net acceleration is going to be up and to the left for a negatively charged sphere released from the origin. So those are the solutions to part A. So now let's understand part B. Derive an expression for the magnitude E naught EO of the net electric field at the origin O due to rods S and T in terms of L, lambda, and physical constants as appropriate. Begin your derivation by writing a fundamental physics principle or an equation from the reference information. So it wants us to derive an expression for the net electric field at the origin. Okay, so let's see how to do this. So let's start with the expression for an electric field. This is going to be equal to K Q over R squared. But because these are rods of continuous distribution, we are going to need to integrate. So let's write the differential form of this. So dE equals K dQ over R squared. So this is the electric field due to a infinitely small number of charges. So let's first find the net electric field component due to rod S at the origin. So because it gives us that the charge density is lambda, we know lambda is going to be equal to the total charge over the total length of the rod, right? Uh, so we'll just denote that as L for now. And this is in differential form, this is going to be dq over dx. So that means dq equals lambda dx, where dx represents an infinitesimally small um, length along the rod, and dq represents an infinitesimally small charge element located at position x, where x ranges from minus 3L to minus L along rod S. So that means the distance from any point on the rod x to the origin is going to be um, 0 minus x, which is just negative x. So we can plug this into the differential equation we had here. We have dE equals k, sorry, we have dE equals k lambda over x squared dx. And then we'll just integrate both sides to get the electric field. So our bounds of integration are going to be from 0 to E and along the length of the rod minus 3L to L. So we're going to get E equals the integral, and we can pull the constants out of the integral. So the constants in this case are K and lambda, where K is Coulomb's constant. So K lambda times the integral from minus 3L to L, 1 over x squared dx. So and I should probably call this E in the x direction. So this is going to be the electric field, just the x component of the electric field provided by rod S. So then this is going to be equal to K lambda times 1 minus x from minus 3L to L. And essentially, if we plug these bounds into our antiderivative over here, we get 1 over L minus 1 over 3L. This is going to give us this is going to give us an answer of EX equals, so let's see here, we have um 1 over, oh, so sorry, this should be minus 3L to minus L over here. So this should actually be 1 over L, sorry about that, 1 over L. And so we're going to have, let's just do a little bit of scratch work here. So 1 over L minus 1 over 3L, 3L minus L over 3L squared, 2L over 3L squared. We have 2 over 3L is going to be the simplified version of this. So we have K, so we have 2K lambda over 3L is going to be the net electric field in the x direction. Okay? But we have to remember, this is only one component of the electric field. But this actually also helps us understand the electric field supplied by rod T. Because rod S and rod T are symmetrical to each other, so rod T is symmetrical along the y-axis, it actually creates a matching perpendicular field component along the y-axis. Because both rod S and rod T are of the same length and they're equally spaced from the origin O, the rod T provides the same magnitude of electric field except along the y-axis. So the magnitude of EY is going to actually be equal to the magnitude of EX. So I'm just going to write magnitude, just for clarity, of EY is going to be equal to the magnitude of EX, which is, as we just derived, 2k lambda over 3L. So now that we have the x component and y component of this force, we should plug these into the Pythagorean theorem to get the net electric field. Sorry, I said force. I meant now that we have the x and y component of the electric field, we should plug this back into the Pythagorean theorem to get the net electric field at the origin. So the electric field at the origin is going to be equal to the square root of the square of the magnitude of electric field in the x direction plus the electric field in the y direction. So, and this is just going to come out to be the um, root 2 times our result here, root 2, so 2 root 2 k lambda over 3L. And that is going to be our answer for part B. Okay, so now part C. So part C asks us, rod T is removed. Rod S is then moved such that the right end of rod S is at origin O. Rod S is then moved with speed v in the negative x direction as shown in figure 3. So now rod T is completely out of the equation and we don't have to worry about it anymore. So, and rod S is moved towards origin and is moving the negative x direction at a constant velocity v. Okay, so it's asking us, on the axis shown in figure 4, sketch a graph of the electric potential at the origin O due to rod S as a function of distance r between the origin and the right end of rod S. Okay, so let's first develop an expression for the electric potential at the origin due to this rod. So, as a function of r. Okay, so the expression for electric potential is going to be, and I'm pretty sure it's right there on the equation sheet as well. Let me open that up real quick. So on the equation sheet, it tells us that the potential is equal to K times the integral of dq over r. Well, similarly to how we substituted dq for lambda, we can do when deriving the electric field, we can do the same thing here. So we get that just as we did here, we get that dq equals lambda dx. Okay, and for our bounds, because rod S moves in the negative x direction with speed v, its right end is shifting at a distance x equals minus r, and its left end it's shifting at a is shifting is at x equals minus r plus 2l, because you have to add the length of the rod, because the left end will be 2l further away, because that's how much longer the rod is. So if we have the right end be at position minus r, then the left end is going to be at position um or we can, if we take the absolute, the just the positive value of this, it should simplify our calculations. If we have the right end at position r and we take the left end to be at position r plus 2l, if we take the absolute value, it should give us the same result regardless. And we can substitute what we got for dq in terms of r. We should probably write this in terms of r instead of in terms of x. And so we go r plus 2l, and we have 1 over r uh, lambda dr, and lambda can come out of the integral, and I'll just simplify things down kind of quickly here. And we have k times lambda times the natural log of r of from r plus 2l. That's the antiderivative here. And this is going to give us a final expression of k lambda ln r plus 2l over r. And if we simplify this down, if we simplify the fractions with the natural log down a bit more, we're going to get a final expression of k lambda ln 1 plus 2l over r. So to draw this graph, the most important thing we have to understand here is how our potential is related to the radius, how far away we are from the rod. And so we should see how the potential behaves as r goes off to infinity, because that's what's happening here, right? The rod is starting at the origin and it's just going off towards infinity. So r is going off towards infinity. And as we can see, as the potential approaches infinity, if we take the limit of the potential as it approaches infinity, we can see that it's going down towards zero. So we're going to have a sort of asymptote at zero. And if we go in the Desmos calculator and sort of graph this function, um, we will see that it is a continuously decreasing curve that is concave up. So I'll graph this function really quickly to see how it sort of looks. So the natural log of 1 plus 2 over x, x because that's how Desmos wants it, and we can see that it sort of is decreasing like this. So as r approaches infinity, the potential approaches zero, and it is sort of a concave down function. So this is how we can sort of use Desmos to understand how these graphs look and just replicate that on our paper, which is an important test taking skill now that we have all these tools available to us. Now for the final part D. Okay, so let's go on to the next page for part D. So, part D, a new, thin, non-conducting charged rod W has the same length as rod S. Rod W has uniform negative linear charge density minus lambda and is oriented along the y-axis. Rod S and rod W are initially held fixed with one end at the origin. Starting at the same time, rod S is moved with speed v in the negative x direction, and rod W is moved with speed v in the positive y direction, as shown in figure 5. Indicate how a sketch of V0 or of VO, at the origin O due to both rods S and W as a function of R would be different with the sketch made in part C. Briefly justify your answer. Okay, so instead of just having one rod, we have two rods now, and both of these rods have the same magnitude of charge density but different signs. So rod S is positive lambda and rod W is minus lambda, and they're both of the same length. They start at the origin and they're moving away at the origin in different directions, but at the same velocity. So we can actually think about this without having to do any math. Let's think about this a little conceptually. So because potential is a scalar, we don't have to deal with direction like we have to do with magnetic field. We only have to really deal with sign. So because these rods are of the same length, the magnitude of the potential at the origin is going to be the same, because not just because these rods are of the same length, because they both travel with the same velocity and they start in the same spot. And that means at any given point of time, they're going to be they are going both rods are going to be the same distance away from the origin at any given point in time. And because they're the same distance away from the origin and they're of the same length, that means the magnitudes of the potentials at the origin due to these rods are going to be of the same magnitude but of opposite sign. So that means they're going to cancel out. So that means the net electric potential V naught or VO will be 0 at the origin for all distances r. And for the justification, it's just what I said, is because um potential is a scalar quantity, and because both rods are of the same length, um charge density and are at the same distance from the origin at any given time. Since, yeah, sorry about the wording here, I know it's not the best, but since they their charge densities are of opposite magnitude, the potential cancels out. Okay, so I know this might not be the best way to structure the justification, but hopefully you understood the essence of the idea behind that. And that is it for question 2. Thank you very much for watching.